Hello everyone, this is the second video I am making on the topic of audio processing with Python, so I will put a link to the first one in the comments. So this time we will continue our journey of learning to use Python for creative audio processing. The topics that I will be covering today are complex waveforms, basically mixing two or more signals, binaural bits. We will write a short but powerful script that can generate binaural bits audio files based on our choice of fundamental frequency and desired brain wave pattern. We will see that mixing signals can result in combined amplification levels, which, if left unattended, will result in a digital distortion when trying to create a wave file. I will show how to work around this problem by setting each component signals his relative amplification level, allowing their amplitude sum to stay within the range of -1 and 1. We will also see how we can normalize our signal, which is a faster, easier approach to dealing with the amplification problem. After this, we will create a simple cluster generator. This is a very nice concept of mixing hundreds, if not thousands, of detuned signals together and playing with the result. This will be a good place to mention the fast Fourier transform algorithm and implement a simple FFT analyzer. Next, I will go on with the general idea about tone perception and how harmonically aligned components result in perceived oneness, with each component perceived as an overtone versus the perception of a fragmented set of intervals when generating a non-harmonic set of components. So after this, we will write a script capable of generating a string-like tones using a simple harmonic series of frequencies and setting their relative amplitude with a couple of slope functions. This will give us a very powerful synthesizer, which we will refactor again to create a wavetable synthesizer. And last will be a nice concept that I am working on. The abstract is to analyze audio sample files, performing FFT analysis on them, and extracting a list of component frequencies, then using our wavetable synthesizer to resynthesize a wave shape whose characteristics are extracted from the audio sample. This will be a cool experimental tool that I'm sure that you will love to try out and use. So before we start, I encourage you to pull the Git repository of this project. I will put a link to the GitHub repo in the info of this video. And for everyone who enjoys this topic and my videos, please consider giving this video a like and subscribing to my channel. Okay, so let's start. So let's start by seeing again how we can use Python to generate signals. I will open this with Visual Studio Code like this and open a terminal. Okay, and in this terminal we can just run Python and with the name of the file like 01, you can press tab and this will run the script. So let's see the first script. This will just generate a sine wave. We can a little bit expand on it. First of all, this is a little bit longer because I've added here the option of us receiving external arguments from the terminal. So we have like default values. We have a basic default frequency of the sine wave and a default length. But if we want to start this script, we can supply two arguments and it will correspond to the length and the frequency. So until here we are just like setting. First we import all the modules and libraries we saw in the last video, and this is another one, the system module that we use to get the supplied arguments. So let me just show you what this is doing. So as I said, Python 3 and the name of the file. So if we don't give it any more information and just press enter, this will first show us the waveform on a graph, and we see it as a very tight block because it's a high frequency and there's a lot of movement here during these 5 seconds. So we need to zoom in order to see that this is a frequency. Okay, So, and after we close this part of the code is first it prints this line, rendering and given the frequency and the amount in seconds, .wave, and then it saves the signal as a wave file so we can hear it, and it will be in this folder. So basically this is just like bringing stuff in, and this is like setting what we want. Yes, this is the frequency and this is the length. Here is just like so we can supply it from outside. As I said, the first one will be length, so we can give it like give us 2 seconds, yes, of this frequency. Okay, so now I have a problem here. I've changed it. Yes, sorry. So if I'll do it like this, so this arrow might go. Yeah, so this time it's 2 seconds, and this is 267 hertz. If you want to hear it, this computer is not connected to my recorder now, so but this is the file, and okay, this is just like a mono file. Okay, so until now this is what we learned last time, and now we can move on to the next script, which will create the binaural bits. It will work quite the same, but it will use this table. I made this in a dictionary. Articles and stuff will divide like the brainwaves functions that we want to entrain with these tones. They divide it to like 5 or 6 bands, like deep meditative are the slow ones, and higher ones will make alertness. So maybe I will create some binaural beats and add them to this video, so everybody will be relaxed and will gain their learning capabilities. So yes, this will be a nice test. The alpha brainwaves, we want to entrain our own brainwaves according to the difference between 2 tones. Yes, this is what is going on here. When we will create the tones now, we will create 2 tones. One is a sine wave, another one is also the sine wave, but the frequency will be with a difference. Okay, there's a difference in frequency, yes, between what is going in the end to our, here if we see the wave file is writing this S, and this S with these 2 lines we are stacking together 2. Instead of it being 1 signal, we are putting 2 signals, but every signal is going to a different stereo channel. This difference is something that we are calculating here, and this is just like my calculation. You can experiment with it a little bit and just like test it and see how it feels. So what happens here is that we are asking from the user to supply arguments. The first argument is the length, so we want maybe like 10 seconds or 1 hour of binaural beats. And then the second argument is the base frequency, which will be like the tone that we are hearing and not the frequency that we are trying to be entrained by. This tone cannot be too high or too low. It's supposed to be somewhere around like 100 or 200 or less or more hertz, but not too far away, because this range, this is the strongest and most powerful effect. And then the third argument is like a string that you will enter, which we want to harmonize our brain and soul with this script. And this is like which one we are selecting. If we want like the gamma brain waves, or maybe we'll do the theta, the theta. I want to try it out. Okay, so I will supply this word. When I will run this script, yes, I will do something like this. I will do Python, and then let's tell it like 150. This is the frequency we want to be to hear, but the difference between the frequency will be calculated here. Yes, it's not calculated. It's set in the beginning, like I've just selected by this like article in the middle. Between 4 and 8, you can make it like more interesting, I'm sure, but I just wanted to show you how to generate it. Like the theta brainwaves are 5 hertz, so the difference between the left ear and the right ear will be 5 hertz, yes, because of frequency plus difference, this. So that's it, and I will generate this. I have to put this word, theta, like this, theta, and enter. And yes, could not convert string to float. Sorry, I forgot about the length. Yes, sorry, yes. So it was okay before, like this, but Yes, we need to do it something like this. Okay, so 60, yes, the first argument, this is an integer, and then the float, this has to be the other one, and the last one, it will be okay, I hope. So let's run this, and this rendered the theta binaural 100 Hertz and 60 seconds. Let's see. So this is the file, and yes, this is very powerful. Okay, so this is quite simple until now. So I hope you like this, and this is how to create like two tones together, but each tone, each signal is going to a different channel, so we don't have any problems. Each one is taking like the full capacity of the channel, and there is no interference between them. They are going to start interfering one another in this script, in the mix signal. So now the whole point is to mix the signals together. We want them to coexist in the same signal. We want to create one signal and then like combine them mathematically. This is like the main reason that we are using the NumPy arrays, because they know how to create like products of what's happening here. This is very easy, you know, you're creating a signal, I'm starting, but just creating it full of zeros, so it's, you know, like just zero information. And then each iteration in what happens here is just like adding another layer of a signal on top one another, and then we will see what happens. Let's see what the arguments are. One is length, and this is again a float. And the other one is a comma-separated string of frequencies. So when we will run this script, we should be able to Python and then this, and then we want to put like the length. So like let's do 1 second, because why not? And then a list like 1 Hertz with 10 Hertz and 100 Hertz. Okay, so the signals will be far apart from another, so we can maybe see them. So yes, this is what happens here. The first one will do just like, we are seeing 3 signals combined, and you are seeing one big wave, and this wave is like the fundamental frequency of this collection, but we'll talk later about the meaning of fundamental and more the context of overtones. So in this case, it's just the lowest frequency, and there's another frequency here that yes happens 10 times in this second, and then there's the really fast one that's happening like 100 times in this second. And if we'll take away just like the middle one like this, so we will run it and we will see like this is just one frequency and another one is the faster one. So again, this is very powerful because we can create a lot of combinations in this way. And like intervals and harmony are like the basic stuff that will have a profound effect on our feelings, you know, with music. So it's actually like really interesting. So, but there's a big problem with this script, and maybe you saw it and maybe you don't. I'll just generate another one. Maybe you will see, and I will explain why there's a problem. But like, even though this is really nice wave shape, it will be supposed to sound interesting, but if we'll try to listen to the files that this will generate, we will, this is totally chaos, you know, this is really bad. So why is it happening? Well, actually, if we look at the amplitude that our signal is showing here, we see that this signal is like way beyond the range of 1 and -1, which this is the desirable range that we want before we are running these lines, you know, because these lines are supposed to like put all the information inside the capacity of a standard wave file. If like we are going to exceed the capacity, so it won't work, you know, it's the signal will be distorted in a digital way, and this is why it sounds like so chaotic. So anyway, we are supposed to understand this, and I've written another fix or workaround this in this script. So the whole idea is what happens here, which is different. I think maybe most of the stuff otherwise is like completely the same. Like maybe if I'll do it exactly in the same place, we could see that there's almost no difference except for one small thing here, which is, you know, the array that we are generating. Yes, it's a sine wave each time. Yes, we are giving it a list of frequencies. Actually, this is also, but this is a problem that I forgot about, like to add these brackets around here. Now it's okay, I think. But in this place, what happens is that like each iteration on this loop is dependent on the amount of frequencies that we want to combine. So what I've done here is just like to measure how much frequencies we have, yes, with this len of frequencies. And according to this, I'm dividing the amplitude of each signal by this number. So they are all going to be in the same amplitude if we'll try to run this script like this time. So let's try and see if this will be with no distortion. So we can try to do this like like this. So again, this will be, first is length, yes, this one is a float, yes, and then a comma separated frequency, yes, and this is the list comprehension line is generating from this string, yes, that we are receiving as arg2. It's going one by one because it is splitting the string on the commas. And then it goes one by one and converts it to a float, and saves all of it to a list of floats. I will run this, and we see that we are in the range of 1 and -1. And now, if I'll try to listen to this, this actually sounds a little bit like the church organ. So we can actually ask for like an insane amount of frequencies together. I don't know if there's any limitation on it. Well, you know, actually there is, because there is a resolution of how many bits it can remember after this will like decrease so much volume, so no resolution will left to tell what is the difference between the different places on the signal. So but this will be totally okay, I think, and yes. And actually sometimes it doesn't even get to 1 and -1. It depends a lot about how harmonic are the frequencies that we are asking. I will show you later a better way how to do it. So anyway, yes. And you can tell immediately that this is like totally more digital sounding. Okay, so the next file that I want to show you, the next script actually, is like a cluster generator, because you know it's not that different code-wise to do a cluster generator. We will supply this, the length and the frequency, the base frequency, and then we can tell it like how many signals we want. You know, instead of just writing each one, we're just telling it how many we want. And what happens with Q is interesting. We are using the number of the iteration, yes, so imagine like we're in the 0 location times, well, it doesn't matter because it will be 0, so again, let's try 1, so 1 times, and then Q, which is, yes, will be a number, like 1, and then each time it will be 1 by oscillator n. It will divide this number by the number of oscillators. So what is the point? Like if we are generating 100 oscillators together, there will be a difference between the base frequency and the 100th oscillator. There will be a difference of 1 Hertz. So they will be detuned accordingly. Let's try it out, because I'm sure it will be better than trying to explain it. So Python, and this time it's number 5. And as we said, we need to supply this, the length. So like, let's try 2. And the frequency, let's try 200. And the number of oscillators, let's try 1,000 oscillators, 10 Hertz away. Okay? So let's try. And you will see this. Most of the time, you will see that there's like a peak volume, and then this most of the time will be quite weak. So I will try to hear this and play with this a little bit, because this is much more playful. So yes, not so much. So let's try to be a little bit more aggressive with this. So I think that like 1000s are okay, but let's try 100 difference, and we will see something like this. Let's try to hear this. This sounds like, looks like a bass drum, but it doesn't. Yes, it's a little bit. Yes, it sounds like a bass drum, and we can try like doing something like this, and we will make something like this. Yes, let's try. So this is weird also. Let's look at it a little bit, because this is, we are trying to experiment here with like sound synthesis in a software oriented approach. So we are going to get a lot of weird stuff. So this is the point. Yes, let's try to increase this to like 5000 and see what is going on. Yes, this is starting to be more weird. Let's listen to this. Very interesting. Maybe if we pull down the bass frequency like to 500. Interesting. Let's hear it. Okay, so this is between like weird and like interesting, I guess. Maybe this will be the one that will... Yes, I can see where this is going. Maybe we will try to push it up a little bit like to here and to see what's happening, because this is very hard to create a wave shape like this, like very creative. Yes, maybe not this one, but maybe if we will try hard enough, we will find something. So we will move on, and this was the clusters script, and let's look for the next one. This is log amplitude. The point here was to use a different algorithm. First of all, I quite looked for several approaches in solving this in a nicer way, but I didn't have too much time like to really go deep and search for the solution. So if someone can find a better way, I would really like to know how we can create a logarithmic difference between all of our overtones over here, but without having to create a normalize function that will deal with scaling our amplitude to the 1 and -1 values. With this, what happens is basically more of the same. A sine function using each time we are asking for a fundamental, and this time, because I'm using with this, yes, this is the algorithm to create the overtone chain of what happens when we are talking about string instruments. You know that a string is a very special case of a vibrating system. It is held between two ends. Because of this, it has like a perfect harmony matching, which I really think that people kind of left out, where like Pythagoras said stuff was, and actually they are happening over there in the harmony of strings. There is a lot of wisdom that can help us understand our life and the world, and not just like tune our guitar better, but like understanding ratios of coexisting components. Yes, this is a perfect system to actually realize how togetherness and coexistence can be, like just by hearing stuff. So this is what happens here. For each iteration in the, you know, n of overtones is like the number of overtones we want on top of this fundamental frequency. So each overtone will be like the base frequency times I, which is the number of the current overtone, plus 1. So this will be like, if the base frequency will be like something simpler, like 100, so the second one will be 200, and then it will be 300 and 400 and 500, and all of these full numbers together in a chain, and each one of them will have a different amplitude. So this will create a wave shape, and then I have to normalize it. Normalizing is just like a function. It's like taking the minimum current, it looks on the signal after it happens. It's not like I knew how to do it. I'm just looking on what happened after I mixed all the signals together, and then I'm just compressing it to match like the desired scale, which is 1 and -1. And this function is a little bit more complex because I found that sometimes normalization functions work better on samples and signals that are not completely symmetric between the upper part and the lower part, but sometimes it works better in a simpler form. So anyway, this is the function, and it is like cheating, but who cares? It's like for music, so that's okay. Afterwards, I'm drawing another bar graph to see the different overtones and their relative amplitude, and afterwards we will see the complex waveform, and then it will create it, so we will hear it. So let's run this with the default values. Yes, I'll save this and we'll do a Python 3 and then something like this, and we won't supply anything. So this is the fundamental frequency, and it's like relative volume, and the next one is like half of it, and this is a third of this, and a fourth of this, and a fifth of this, and they are all together. And because they're mixed together, it will be more than 1 and -1, so this is the normalized function I have shown you. And now they are after this normalized function, so they are okay. So this is like this. And actually, if I will play this is a nice already bass tone. Yes, it's a very nice bass tone that if we just change like the amount of overtones, is very like changing the cutoff frequency and changing its like total characteristic. Like just try it, like we'll do like 1 second of 100 and put like just 3 overtones. Yes, so this will be like more dark with less high frequency sound. Yes, this is it. And but if this, I can close this. But if I will play, if I will generate like with 20 overtones, which is more than enough, yes, so this will actually sound much brighter. Okay, so this is this synth, and it's very nice because you can create beautiful bassline just with those tones. It can be very, very nice. If you can go even like crazier, you can say that the bass frequency is 1 Hertz, but it will have 200 overtones, so it will look something like this. And I bet that you don't have like a very easy way of creating like crazy stuff like this with your analog synth. So let's continue. We are talking a lot about like the components of one signal and a very nice way of like seeing it. Yes, before in the latest one we saw like a bar graph that shows the relative proportion of amplitude of the components, but I'm talking more about analysis of the signal. So with this script, we can analyze signals and look at their overtones and components. And this is called the fast Fourier transform, which is a very very sacred like topic of like mathematicians. This is one of the most interesting and most like important things that we can use. And my understanding of it is like basically it looks to me like trying to tune a guitar with a tuner. This algorithm is like looking on a window of a signal, and like a window of a signal is like a small slice of it, and we can tell it like just look on all the signal from the beginning to the end, like like think about like a 1 hour long of signal and we are telling it to FFT it, we will have a lot of information in one view, so it won't help us so much. So the idea here is mainly like to capture a small fragment of the sound, like a window or buffer, and analyze it fast, and then it will give us the spectral components with their relative amplitude as an image. And this is like 99% of the graphic equalizers that you are using to see, like sometimes the bars with the bass and the mid and the treble on stereo systems, you know, the dancing lights. So this is like some kind of FFT in some way, but not exactly, but this is very similar. So this algorithm, as I said, it's very complex, but you can try to imagine that we are going on very, very small steps and changing a reference frequency and summing it together with our window fragment of signal. And we are checking to see if there is a decrease or increase of gain to our reference signal. And then because we cannot do like endless amount of frequency, we have to go in steps. So this is a little bit of how I imagine this algorithm. But with this way, you can just use it to open like all sorts of files. So let's try it out. I have a little bit of maybe we just generated, you know, like this file. So if I will take this name like this, and we will run this script. Python 3, and then this is 7, and enter, and it will ask for the file name, so I will paste like this, and this is the analysis, and this is actually what we created. And you can see that like we didn't create it like a musical instrument would do it, that like the frequencies we will see with the real sample, they are much wider because there is a like an inner vibrato of the overtones. I can show it to you. I think I have it here in this folder. I have like a sample like this one. Yes, so this is my voice. So I will take it just like this if I'll run it again, and I will write like woods, yes, woods, and t.wav, and this is like my voice. And you can see that what I was talking about, that like each component, it's much wider, it has like a range, it vibrates, it is not like static so much. And with this algorithm I will show you later, as I said, how we can like just do something like this and select like the highest level components and then get their like peak frequency and then regenerate them with something like one of the scripts that I've shown you until now. So this is actually what happens here. There are two more scripts. First one is what I've called wavetables, which is like a refactored script of amplitude, range, and mixed signal scripts that we saw. But this is all like wrapped up in a class, and we can use it a little bit different, much more easily and dynamic. So what happens here is just like we are creating a wavetable, yes, and we will set him up all sorts of stuff. You can see that actually in this script I've added much more formulas to create or different shapes of amplitude ratios between the overtones, so we can change between linear change, logarithmic or circular or sigmoid shapes of difference between the amplitudes of the components. So this class has also the normalize function, and it has also a make signal and a render function, which these ones are the ones we are going to use. So let's try to do this. You know, this is, at first it's just like very easy. It just gets again the same amount of frequencies, and just like try it, So we want to run this Python 3 and then import wavetable, and we will do this and the make signal and the render. So I hope this will be yes. Okay, so this was like the wavetable class, and we can do like mixing of what kind of we can use it in another script to just create many wavetables and use them. It's amazing. So now the last one is going to be what I call the physical renderer. I won't try to go into it too much because the general idea is what I've said is going on. You can see actually from this script, the synthesize, you can actually try to understand what happens here. And in this script, you can just run it and it will create something. So for now, we can try to do it to this sample, like maybe this one. So this sample has like overtones as we saw in the FFT analysis. So I can open this sample. Yes, so I'm setting what sample I want to open, and then I'm opening the file and I am preparing it, if it's a stereo file or if it's a mono file. I'm doing all the changes that is needed, and then afterwards I'm doing an analysis. So this will create FFT, what I've shown you, but a little bit more complex because I've checked it and I've thought that it's better to filter a little bit of the signal, to cut off a little bit of the low and high ends. So most of the frequency range will be in the center. So this is what I thought will be nicer. And then it's generating a wavetable by supplying it the FFT analysis. It takes just the highest peaks and it creates a list of frequencies. And then it makes the file. So I'll try to run this, but this is, very experimental, and most of the time the sounds it creates is very interesting and non-conventional, So I will open a new terminal and I will run this Python 3 physical renderer like this. And because, this lines here just asks me for the file name inside this folder, but you can change it to what folder name you want to open the files from. You don't need to add the .wav, just give it the name of the file, like this, and we can do it like T1, and it renders the WAV file. So the first file is this one. Yes, this is my voice. And this is the rendered spectral analysis of this voice. So this is actually, does have like the characteristics of the sound that it was generated from, but it could be much more, specific if I will decrease the window function, because as now it just looks on all the WAV file at once and analyzes it, but there's a lot going on in one WAV file. We have to take like a very small fragment of it in order for this to be more accurate. I hope this was good for you. I really enjoyed it. Please try to support my channel, Metallic Code. I really enjoy doing these videos, and I hope that you learned something, and for the next videos we will continue to do like very nice things with code and sound. So hope to see you next time. Goodbye.